Okay, now I have already alluded to how we're going to do our working for this test in terms of using the sample as evidence, but let's just try to put a visual to it. I've got a claim about my population. I'm claiming that the population mean age is 50. So maybe I've got, a group of customers. There's been a claim that the average age is 50 of that customer base. So we have a claim about the population. Our status quo is the equals. It would therefore be that mu is equal to 50. I want to test that claim. I want to see if, in fact, it's changed. So I could certainly set up a hypothesis test. The idea is I'd write down my null. I'd write down the alternative. Of course, that would just be mu not equal to 50. Now, we've said when we run one of these tests, we assume the null is true unless we prove otherwise. So the idea is that even though we don't know what that full population looks like, we would be assuming that the true population mean is 50 unless we get evidence to the contrary. Now, if the true mean population, or true population mean is 50, remember, we could then say something about the sampling distribution. If the true population mean is 50, well then our sampling distribution of the mean would also have a mean of 50. So we can start to say, well, if this is true about the population, this is what our sampling distribution would look like. And so when we come along and take our sample as evidence and work out our sample mean and find, say, that it's 20, well, what really are the odds of getting a sample mean of 20 if the true population mean is 50? Is that likely or unlikely? So we have a look, and the idea, of course, is that if it's not likely, if we're saying that if the true population mean is 50, that our sampling distribution would also have a mean of 50, and therefore our sample mean when we take one sample should be fairly close to that value. If we get something that's very different, we're saying it's not likely, and so the idea is that that would cause us to reject that null hypothesis. Likely, not likely, we need to be much more specific than that, and we can be because of all that sampling distribution theory. Remember, if we know the distribution of x, we know the distribution of x bar. What we're saying is that if the null is true, the mean of our sampling distribution would be 50. We can work out what that sampling distribution looks like, and we can actually find where our sample mean in the one sample that we've taken falls relative to that sampling distribution. And if it's, say, in one of those tails where it's very unlikely that we would get this kind of result if the true mean population distribution was 50 and then therefore our sampling distribution had a mean of 50, if a result of 20 is in one of those tails, if it's unlikely, well then that would be sufficient to reject. If our sample mean was, in an area that was quite likely to occur, maybe not exactly 50, but within that sort of range where it's likely just to be the result of sampling variation that maybe gives us a sample mean of, 48 or 51, well then that wouldn't be enough evidence to reject. So pretty much what we're going to do with our sample, we're going to create the sampling distribution based on the assumption that the null is true. We're then going to see where our sample actually lies relative to that sampling distribution and see whether it's the type of sample result that was likely if the null was true, or whether it's an unlikely result to have happened if the null was true. And that's how we're going to decide. And we are going to set up some very specific boundaries where if it's one side will reject, if it's the other side will not reject, and they're going to be based on quantifying that uncertainty and therefore using probabilities. Okay, so the point we're at is that we make a claim about a population. We're going to test that claim using a technique known as hypothesis testing. So in fact, we're going to create a null hypothesis and then an alternative hypothesis based on a population parameter, such as population mean. The null represents the status quo, the alternative represents the possible change. We take a sample, and that sample becomes our evidence to test. We're going to run the test on the basis that the null is true unless we prove otherwise. Now, that assumption that the null is true unless we prove otherwise allows us to say something about the population, which then allows us to say something about the sampling distribution, such that we can compare our sample result that we did get to what we should have got if the null was true. We're going to need to be a bit more precise in terms of, what's likely, what's not likely. So in that previous slide where we said if the null was true, the mean of the population was 50, and therefore the mean of our sampling distribution was also 50, such that if we then took a sample and our sample mean was 20, if that's a long way away from 50, if that's in an area that's unlikely to occur, well, that might be sufficient for us to reject, but we haven't really quantified what's going to be likely and unlikely, so we'll need to do that. Now, the type of terminology we use, we're going to talk about something called a reject region, a rejection region, and it could be plural. So the idea is, let's say we're doing a test involving equals versus not equals. The mean is equal to 3, the mean is not equal to 3. The idea is that when we have this equal, not equals type situation, it's referred to as a two-tailed test, because when you create your sampling distribution based on the null hypothesis to then compare to the actual sample result that you have, it may be that if we get a really small sample mean that's a long way below 3, that would make us reject. But it could just as easily be that we get a very high sample mean, something way above 3, that makes us reject. Because remember, the alternative is just that we're not equal to 3. It doesn't say which direction we're going in. So it could be either direction. And when we therefore create a reject region, we're going to have it split into two, such that if our sample mean is a long way below the sort of hypothesised population mean, or a long way above, then that would be sufficient for us to reject. How big will this reject region be, or reject regions if it's split into two? Well, the idea is that you would only reject your null hypothesis if, say, the sample mean was in the maybe 5% least likely, or maybe the 1% least likely. So you set up that level of where you're going to reject, and that then translates into how big the total reject region is. So, for example, if you do a 1% test, you would be saying, I'm going to reject the sample mean if it's in the least likely 1% to occur if the population mean really was true. Now, if it's a two-tailed test, that 1% total reject region gets split into the two tails. Of course, if you're doing a hypothesis test involving direction, where you're not just testing to see if a result is different, but you're testing, for example, to see if the mean is, say, greater than 3, or maybe you're doing a test to see if the mean is now less than 3. Those sorts of tests where you have inequalities, they're known as one-tailed tests, because you know the direction you're specifically testing in, and so you only place that reject region in the one tail. So, you know, if your reject region is 1%, that entire 1% goes into the tail area. It doesn't get split across the two. Because, let's look at this one as an example. If your null is that the mean is less than or equal to 3, that's your status quo, and you're testing to see if the mean is now greater than 3, the only way you're going to reject the null is if your sample mean is high enough to support that alternative. So you're only going to reject the null if you get a sample mean that's above 3, and in fact in that, say, 1% area that's least likely to occur, compared to if the null was true and therefore the mean was equal or less than 3. So two-tail, one-tail, from a sort of very technical perspective, it just comes down to whether you're doing an equals, not equals test, or whether you're doing a directional inequalities test. But the logic is still very important, and that's thinking about, you know, what kind of sample result would make me reject that null hypothesis. That it has to be something that's away from the null hypothesis, such that it's in that tail rejection area. And when it comes to how big that tail should be, that's when we have these values. We specify how big the rejection region is going to be. It's common to use 1%, 5% or 10%, and we actually call that alpha, the level of significance. And you might be thinking, well, when we did confidence intervals, you know, they were a 95% confidence interval was 1 minus alpha, where alpha was 5%. Well, this actually matches into that, such that two-tail hypothesis tests are actually just an alternative way of looking at what we did with confidence intervals. And I will show you that very soon as well, just that you get the same result. But that's the idea, is that you set up your null, you set up your alternative, you take your sample, you then look at your sample mean and think about whether it's a sample mean that was likely to occur if the null was true, or whether it was unlikely. How do we define unlikely? Well, we set up a reject region or regions, depending on whether it's one-tail or two-tail, and we see whether, say, your sample mean was in the 95% likely to occur, or whether it's in, say, the 5% not likely to occur. And that's how we judge and come up with our conclusion. So, look, there's been a lot of information. We do need to sort of put this all into a practical problem, and I just